and we're very excited.
All right. Good morning, everybody. All right. Terrific. So my name's Connor. I'm coming from MIT. And today I thought I would talk a little bit about some challenges in molecular optimization. So I sort of have this bad habit of trying to cover too many things in one talk, and so I will probably do that again. But as usual, interrupt. If we don't get to things, we don't get to things. But so I wanted to try to cover sort of the landscape of what I see as the major challenges remaining for computer-aided molecular design and optimization. Now, just to get everyone on the same page, these are the kinds of molecules that I'm talking about when I say molecular optimization, right? Small organic molecules for the most part. They're the majority of our approved medicines. We use them in agriculture. We use them in material science. And they're really this very fun modality, right? A very versatile modality that can basically give us this impressive range of functions just by rearranging, in a sense, right, familiar atoms and bonds. Now, we think a lot about computer-aided molecular design and the ways that we can use computation and algorithms to help us arrive at such discoveries and structures more readily. But if you sort of look at the landscape of computer-aided design, I at least find a lot of the practices somewhat unsatisfying. So this isn't a critique of the discoveries that they've made, but it's more a critique of the extent to which computer-aided design truly is relying on algorithms to help us make those ultimate decisions of what to do. So you look around the literature and you see all sorts of anecdotes of the processes people go through, and they'll use different computational techniques and algorithms to prioritize structures. They'll use different scoring criteria, but then at the end of the day, almost always, they hand a big list to some experts, and those experts go through them manually and choose what to do. So you see these sort of processes and methods sections where they talk about taking top scoring molecules, and then they cluster them into 4,000 clusters. They inspect them, and then they pick 17 to make. Why 17? Why 4,000? In this case, they looked at 40 molecules whose ranks span 16 to 246,000. And so, something about this ranking function is clearly not, mimicking, right, actual user preferences. And so I find, despite their successes, I find these workflows, again, fairly unsatisfying. And so I hope there's room to make this a little bit more systematic. This is going to be a little bit of a reductionist view of the world, but we can think about what molecular optimization looks like and what we're really trying to do precisely. I would argue we're usually trying to find the best molecule from a set of candidates according to some oracle, right? Simplest single objective case that we can have. So design space is the set of all possible molecules. We're trying to find the best design, and we have some f of x that's telling us, right, about the fitness, the properties of that molecule of interest. Now, really, we often will use sort of surrogate oracles. We'll update this iteratively. We'll do Bayesian optimization and some model-based optimization. And so we might not have access to some true oracle, but really it's some machine learning model, f hat, that we're using instead, right? And maybe, of course, we don't have to just take the argmax here. We can use different acquisition functions from Bayesian optimization or active learning as we iterate through this process. But this is the general framing that I sort of view molecular design through. And so what I'm going to try to do, and again, we'll see how much time we have. Please do interrupt as we go. But what I'm going to try to do is talk about sort of 4 categories of challenges that make this problem a little bit more nuanced than it seems. So we're going to talk a little bit about oracles, talk a little bit about the design space itself, what that means. Think about the sort of representations that we use in these surrogate models for model-guided optimization. And then in reality, molecular design is not a sequential iterative optimization. It is batched, sometimes not iterative at all. And so that introduces some different considerations that we should wrap into how we think about computer-aided design. So like I said, I'm going to introduce some challenges. I'm going to introduce some partial solutions, and I'm probably going to accidentally start ranting at different points. So bear with me. The first sort of thing I wanted to point out is that as the field sort of really grew to explore generative models for molecular design, it very quickly converged onto a series of very silly oracles. So still the predominant objective functions and oracles that are used to benchmark generative models for molecular structures are things like penalized log p, this QED heuristic, and then these sort of similarity calculations that are trying to mimic the rediscovery of known drugs. So penalized log p is basically just a computed lipophilicity you subtract some synthetic accessibility heuristic, you penalize rings and things like that. But if you just take a molecular structure and you generate a bunch of carbons, you win, right? You optimize this objective function, and so a generative model that just outputs the capital letter C and builds a smile string will maximize penalized log p. QED is this sort of fragment-based method that, again, scores from 0 to 1, this sort of drug likeness. And basically, it saturates at 0.948. And if you have a generative technique that doesn't get 0.948, that's a huge red flag. And if you have one that does get it, great, right? It's a necessary but nowhere near sufficient criterion for having a useful generative model. And so then people started thinking, okay, well, let's apply these apply these generative models to objective functions that are a little bit more complex, right? Things we care about. One of those things being docking scores, right? Docking, a method to crudely estimate the binding affinity between a small molecule and a protein, among other things. Negative is better because it's sort of like an energy. And you can see, this sort of older benchmark table, they were looking at the performance of a few two not great methods, and then one using reInvent from AstraZeneca, which is quite a competitive method. And they looked at sort of the best docking scores they could achieve for the generated compounds under some fixed budgets. And they arrived at these, certain negative 9.8, negative 8.7 for different protein targets as the different columns. And on the surface, you might think, well, reInvent is certainly better than this conditional VAE or this grammar VAE. But if you compare it to the training set of the models, it's not better. And if you compare it to virtual screening of a fixed library, it's also not better. And so a lot of the comparisons we see for generative techniques are internal comparisons. They don't really think about the proper baseline of having training set compounds or virtual screening compounds. And so we still really haven't seen these models robustly sort of push the boundaries of the property space that can be accessed. If you take a virtual library from Zinc or Kemble or PubChem and you draw some like big property convex hull, generative techniques don't sort of in a useful way typically extend that for the properties that we care about.
Do you have a sense of why reInvent isn't even recovering the molecules from the training set that improve the score? I mean, why would that be the case?
No, I don't have a great sense of why that is. Well, one of the things that reInvent does, which will come up later, is it contains a term that prevents it from being swayed too much by its optimization objective, and it wants to stay relatively close to its prior. And so I think perhaps in this case, the prior is trying to keep the molecules looking reasonable, and maybe that's just preventing it from exploring in the way that it needs to. It's a very crude sort of penalty that's applied. Yeah.
This is a similar question, but do you have a sense of to what extent it's the generative component versus the surrogate model that's making like improving docking hard?
So in this case, these are not using surrogate models. These are using sort of docking as just like one fixed oracle function.
Okay, yeah.
So these are sort of directly trying to optimize this docking calculation, not through a surrogate. So docking is a funny thing. It's been around for a long time. It's widely used. And again, docking is typically broken down into, let's say, post-prediction and scoring. And so post-prediction has been sort of approached with really interesting techniques recently. AlphaFold 3, right? One of their sort of highlights is this sort of complex prediction. And so post-prediction and getting the geometries approximately correct for protein ligands binding is making quite a lot of progress. But scoring, actually taking this sort of geometry and understanding what does this mean in terms of binding affinity or quantitative interactions, that is where we still really have not seen much progress. There's this competition, which I think is no longer held. I'm not positive, someone can correct me. Computer-aided or computer-assisted scoring functions. It's a not as nice version of protein structure prediction, the CASP challenge that many people will know. The idea was that it was a benchmark competition to try to see could different scoring functions better differentiate, given a geometry, the best ligands with experimentally validated binding from a set of decoys that had similar structures or physicochemical properties. And so this scoring function, right, is trying to differentiate true binders from non-binders, or at least true binders from decoys. And this sort of bar chart is summarizing the success rate in doing so. So how often is highest affinity ligands contained within the top 1, 5, or 10% of the decoys? And you'll look at this, and you might think that we're doing okay, right? Each row is sort of a different scoring function. Many of them are sort of machine learning scoring functions fit to data. And you might look at the sort of top predictive one and say, okay, well, about a little over 50% of the time, this is including the highest affinity ligands, right, in its top 10%, right? So this is enriching, right, among a set of decoys for a true binder. This is a useful way, perhaps, to find binders. But the data is not well separated or well controlled in these benchmarks. And so everyone is sort of using this data set in a retrospective way. And if you actually look at this paper that reports these, they note that this particular best scoring function was trained on about half of the test set. And so the fact that it gets about a 50% is much less impressive, right, in light of that. And so I think scoring functions, I don't have the sort of solutions to propose. I think it's a very well-posed task of taking geometries and predicting some scalar and trying to use that to find binders. But it's been pretty elusive to find general sort of robust scoring functions that can actually be applied to this high throughput structure-based drug design. And in the current state of the world, because people do still use structure-based drug design techniques, we almost always take the docked poses, take the scores, rank them, but then still ask experts to look at those docked poses. So Brian Schoiked is very good at looking at such poses and has written a bunch of articles about this. What you often find is that the bound poses with the best docking scores, right, which you would hope would mean the highest affinity ligands, are really just artifacts. And you're basically just finding the pathologies of that scoring function. Now, do we know exactly how to patch those holes and fix those pathologies? No, otherwise we would have. But there is something that experts can do. And so there's, I think, some hope in trying to translate those into our scoring functions. So this sort of connects, I think, to a bigger question or bigger point that I would make. And I was a little bit making it in the discussion yesterday, which is that we don't really have good oracles for properties we care about computationally. And so as much as we can talk about computational data generation, there's still a gap between our ability to anticipate properties, useful experimental properties computationally, and what we actually need our molecules and materials to exhibit in the physical world. Ligand binding is just one of these examples, but I think this is true of most properties that we would care about for molecular discovery.
Arguing that the dots of the pose is correct. Yeah. Why doesn't that translate into affinity prediction? Especially for like a generic series where maybe it's kind of the absolute scale is set, and you're just looking at deltas between different molecules. So you think would all be there in the pose.
I think that the sort of our tolerance for what is considered a good pose or a very, very close match doesn't translate well into a quantitative energy that we would calculate from that pose. I just think it's a more sensitive function. I don't know what the actual sensitivity is, right, with respect to sort of atomic positions, but I think it's just a much, much sort of subtler question. And I think we're very tolerant of close matches in pose prediction, but those translate into large differences in energies.
Maybe also along those lines, kind of in this space, how do people tend to think about kind of the differences of enthalpic versus entropic roles in binding, and just that we're docking textures, this very static one?
Yeah, I mean, to my understanding, most people are focusing on almost exclusively enthalpic arguments, and then if your ligand looks a little bit too floppy, you'll try to rigidify it as sort of a separate consideration. I don't think I've seen too much of it being very sort of intimately coupled, as you'd expect. So that's a case where obviously I'm offering no solutions, but just sort of pointing out that I think devising good oracles is a pretty significant challenge, especially in this context.
So what do you think would be most useful to have access to in this case? Like if there were big experimental libraries of binding?
Yeah.
Is that the thing that is needed? Or?
I think big experimental libraries of binding affinities is what's needed here. Yeah. I think it's, perhaps with enough cleverness, one could squeeze information out of PDB bind and the data that we do have. But I think we do just need large libraries of experimental binding affinities to be generated at scale.
Just when you say large libraries of binding affinity, do you mean with structures, or do you think even without structures, just molecules, protein pairs, binding affinities would go a long way?
I think it's unrealistic to expect that we would be able to have structures for bound poses for everything, and so I think it would have to be just protein molecule pairs. And I think we'd be relying on the fact that pose prediction can get us most of the way to an approximate geometry. That's a fair question.
And then just kind of a maybe rudimentary question about binding affinities. What's the uncertainty bounds on it? And also, is it more of a logarithmic scale or degree of binding, or is it more of a
So it's in terms of energy, it's more of a linear scale, but then in terms of like binding constants, that translates into then you end up sort of exponentiating.
And then what's like the error when people do this experimentally? If you run like 50 different versions of it, what are the range of errors that you choose?
Yeah, that's a very good question. I think experimentally, if I had to ballpark it, I'd say probably you're talking about less than like half a kcal per mole spread. I don't know.
Okay, that sounds right.
Okay.
Yeah. Though there's also just different hands producing different measurements in databases. Those are hard to get bigger.
Yes, and there's perhaps confounding factors in experimental protocols for experiments that haven't been designed identically.
Do you think, so most of these calculations are done with VS scores, right? Do you think there's a middle ground where you could maybe try to do FEP calculations instead versus going to experiment?
I think, so I have not personally, we haven't run FEP calculations in the group. In sort of advising and talking to folks at companies, I think FEP has seemed reliable for smaller numbers of protein targets. I think that's, depending on who you talk to, they've had more or less success using FEP to explain quantitative differences in binding across a series. I think I don't think it's at the point where you could sort of just turn the crank, allocate more compute, and generate these larger data sets. But I think I hope there is a middle ground, right, between experiments and something as coarse as docking. But I don't think it's shown up yet. Even your MD, I think, is not great at explaining perspective.
Just wanted to check my understanding here, and please tell me where I'm getting anything wrong. Is that it seems like the issue is pose estimation, which I'm guessing is some sort of mean squared error kind of distance error minimization is not quite the end goal here. And so what you really want to optimize is binding affinity. But is that correct? So basically, like models are trained to do pose estimation. They're not trained to minimize binding or maximize binding affinity.
Yes. Yeah. So post prediction is just saying, when this ligand is in a bound state, what does that state look like geometrically? It doesn't tell you sort of quantitatively in equilibrium with unbound and bound states. How often is it in the bound states? It doesn't tell you sort of on rates, off rates, strength of that interaction. Yeah.
So why can't we just try to predict that the target quantity we care about directly? Like sorry, I just.
No, I think people. Yes, so sort of direct. Well, I think people use geometry as an intermediate for this. I think why it hasn't been successful in being predicted, I think, is perhaps a function of the data, perhaps a function of the algorithms, but there just is. I don't know, a qualitative explanation that I sort of hold internally is that if you're predicting a quantitative binding affinity, that sort of one scalar is the label for this pair of data. Whereas if you're thinking about post prediction, it's a much richer piece of data because just sort of one data point gives you sort of a little bit more information because you've got many different sort of rotatable bonds and many different interactions, and each of those you get a piece of information sort of implied by the geometry of that bound pose. But it's a very qualitative explanation.
And so is there also just more data for that, like geometric?
Yeah.
There's less data, more refining of it.
Yes, yeah, that's also right.
So this, I mean, this general challenge of having no truly robust computational oracles is something that means that I think we're often trying to operate in an experimental space, right? We're trying to use experimental oracles, right? Ground truth, binding affinity measurements directly, or other, optical measurements experimentally. And so that sort of leads into this sort of second consideration of the design space that we're actually navigating when we think about molecular design. Now, I will say I spend a lot of time talking to pure chemists who are less familiar with machine learning, and everybody loves generative modeling, right? Everyone thinks it's fantastic, right? These models are inventing new structures. They're freeing us from the limitations and constraints of these virtual libraries, even though these virtual libraries contain tens of billions. That's not enough, right? Let's go bigger. Let's invent new structures. And so we can do that, right? And people have been doing this since about 2016 for chemistry and before that too. With deep generative models. And so we can do this in graph space by generating this sort of thing that looks like a ProTac to optimize some computational ProTac oracle. We can do it in three-dimensional space by trying to sort of match the shape of this sort of query in blue, and we'll generate this ligand in pink and say, I want a molecule that fits this shape, and we can do 3D reasoning to build it up fragment by fragment. But the problem, right, when you actually talk to people in pharma and you try to use these techniques in practice is that there's a lot of different ways that these models generate structures that do not look useful and are not useful. And so for small molecules, what that looks like, sometimes you get structures that look okay, and sometimes you get structures that look very, very unreasonable. They're syntactically valid. They don't violate valence rules. RDKit, your favorite cheminformatics tool, can parse them. But these are not structures that you can physically make. They're not structures that you would try to physically make and test in the lab. And that's typically due to one of two things, right? Either they're not stable or they're not synthesizable. There's no way to physically produce this molecule to try to test it, even if it were stable. And so these generative techniques, when you apply them to optimization of oracles, can lead you to these very unrealistic and unhelpful ideas. And I'll just sort of as a note, the generative model in coming up with this as an idea, it's not necessarily the generative model's fault, because the oracle or the surrogate oracle is saying that this is a good molecule. So the fact that we arrive at very silly structures as local optima is also sort of a reflection of these pathologies and issues in the surrogate oracles that we're using, or just, normal oracles as well. So we want to sort of address this fact and try to come up with generative techniques that don't have these particular failure modes of lack of stability and synthesizability. And so the one approach that has been taken is using sort of penalty functions or regularizers, or whatever you want to call it, where in the simplest case you might take these different heuristics that have been developed to map structures to scalar measures of synthesizability, and you just modify your objective function. You basically say, I'm not going to optimize my docking score. I'm going to optimize my docking score times my synthetic accessibility score, something like that. The other thing you can do, and this is what I was mentioning for reInvent, reInvent in particular, when it's doing its sort of goal-directed optimization, it's not just trying to maximize the score of its predicted sequence of tokens, but it's trying to keep in mind its prior, which was trained generically on Chembl or zinc, and so it's trying not to deviate too far from what's known. And that does have the effect of keeping the molecular structures it generates in a slightly more reasonable chemical space. But I argue that the most robust way of assessing whether these kinds of molecules can actually be made by chemists, and therefore can actually be tested by chemists, is to do synthesis planning, right? It's to actually go through the effort of taking the structure you've just decided you want to make, or you're proposing to make, and figure out, if I were to make this, how would I do so? And so synthesis planning, right, is the act of trying to take your target structure and come up with the recipe for how you might produce it. So what commercial starting materials are you going to buy? How are you going to mix them? What are the intermediates you're going to isolate? And how are you going to build up complexity chemically from simple things that are in the lab to the final molecule that you want to make that maybe has never been made before? And so computer-aided synthesis planning has been around since the 1960s in various forms, and it operates the way that humans do, which is retrosynthetically. we start with this target molecule and we try to work our way backwards and identify sort of simplifying disconnections until we reach those starting materials. And so we could imagine taking the molecules that are proposed by generative techniques and then using synthesis planning as a filter. And so to do this, we can build up different retrosynthetic programs. In a very brief summary, the way that these work is we need a model that understands how to take a product structure and propose that single-step disconnection. We have to learn what disconnections are allowed from data. So this is something that we train with supervised learning. And we need a way to apply that sort of one-step model recursively, because if you take your product that you want and you do one-step disconnections, you might have a lot of options, and maybe none of those are yet viable. So you have to go further back and further back and further back. And so you end up with this sort of expansion step, and then you get reactants as a result, and you need to then sort of further go back until you do terminate in commercially available starting materials typically. And so these sort of components of synthesis planning, it's not the emphasis of this talk, but these have their sort of own development story over the past 60 years in building and refining these largely now as data-driven models. So we've been doing this too, and we have some software, and we can use this software to filter out the recommendations we get. Now, I also find this somewhat unsatisfying. I guess that's a trend here. Because when we apply synthesis planning models to generated structures, we're effectively trying to do a constrained optimization by doing an unconstrained optimization, and then hoping and crossing our fingers, right? Really, really hoping that we happen to arrive at solutions that are in the feasible region. But I'd say, chemical space is this enormous combinatorial thing. And the subset that is easily synthetically accessible is a small subset. It's a sparse subset. And so we often will arrive at solutions that are filtered out when we apply this in practice. And so if we truly want a constrained optimization, I would argue that we should be doing a constrained optimization from the beginning. And maybe there'll be some good, healthy pushback about that. So generative models for chemistry often reason about chemical structures as sequences or as graphs or as point clouds. And so they pose molecular generation as character generation or atom generation or fragment incorporation. And so we have these different generative techniques, but rather than doing this, one of the approaches that we've been trying to sort of further develop is the notion of doing sort of reaction-based generative design for chemistry. The way that we would physically arrive at this molecule in the lab is through chemical synthesis. It's not through adding one atom at a time. We can't do that. And so if we reason about molecular structures in terms of the experimental procedures or processes that make them, right, then we can sort of pose our generative task in this constrained space. And so this is sort of part of then a class of techniques where we're trying to do procedure-based, right, or synthesis-based design of new molecular structures.
On the previous slide,
Yeah.
you said you don't have a low volume chemistry.
Yeah.
But you do have this library of possible reactions. What's the gap between these two? The latter seems like a partial world model for chemistry in a sense.
Yeah, so we have large databases of tens of millions of chemical reactions that have been experimentally performed. And those give the sort of partial insight into what new transformations would be possible. When I say new transformations, there's different ways that a transformation can be new. So if I have a reaction that's A plus B goes to C, if I have a very subtly different A prime, I might assume or infer that A prime plus B can go to C prime. I can sort of make that analogous modification. And so the world model that we sort of build kind of looks like that, right? We try to make these inferences about how molecules react, what transformations are possible. And we need some level, though, of generalizing from just the precedent reactions as they've exactly been demonstrated to what we think is possible for new molecules and new substrates that haven't been seen before. So there's sort of a layer of learning on top of the data that we use to approximate a world model. But that, of course, it's a machine learning model, and it has its own pathologies and issues.
Can I participate in the healthy pushback?
Yeah.
So
that, I feel like you're sort of, you've swept something under the rug here, which is that you're talking about the synthesis planning and retrosynthesis stuff as though it is somehow easier than developing good oracles. And I mean, maybe empirically that is true in your experience, but I think of retrosynthesis as being just as hard as having good oracles in the first place. So, if we are looking at this problem of like molecular optimization, I mean, why is it not better to just think of it as molecular search, sample, and just filter, with things that you know are in zinc, or like, I mean, there are these huge databases that you can just query and say, like, is this something that is easily synthesizable?
Yes, well, I'd say, so zinc, these virtual libraries, they're not, they come from this kind of reasoning, right? Like just that someone else has done this prior to us.
Yeah, but I'd say it's like more primitive than what you're proposing, right? It's like very small modifications of compounds that people have actually made, where they know exactly what reaction they would do. Like you can order them, right?
Yeah, so I think there's arguments maybe about how, well, there's intellectual property arguments. A lot of pharma companies avoid these pre-enumerated catalogs because it's not good for patenting. But then I think there's also a question of whether there are chemical spaces that are sort of underrepresented based on how those libraries have been built up. I will say that, in a practical perspective, like when we actually, in rarer cases, have bought compounds for experimental testing, ordering them from a catalog is fantastic and very convenient. And I think is a good way of collecting some information that then tells you, okay, do I need to deviate from the catalog, or have I actually found a decent solution here? I don't think they're mutually exclusive, but I do think that rarely is it the case that if we're trying to do therapeutic discovery, we would end up exactly with a lead compound going to clinical trials that we got from zinc. So at some point, we will have to deviate. So the question, I guess, is just, is that early or late in the search?
Yeah, but to make the question precise, do you think that retrosynthesis as a problem is somehow easier than the problem of like building a good oracle and then just filtering?
Yes.
Okay.
Yeah.
And part of this is because of my unfamiliarity with the constraints on kind of reaction by reaction. How specific, like, do you have a fixed set of reaction steps that are available, and then they each have their like very specific constraints on what they complete on, add on? How easy is it?
So there's different ways of trying to define like what is the space of feasible reactions, and this is where what we're doing here is basically like a generative version of enamines real space, or we basically equip some policy with access to a large number of commercially available building blocks, as well as these sort of expert defined templates, which do this kind of thing of saying, okay, here's the kind of way that you can bring these together. These functional groups will form a carbon-carbon bonds, and as long as you don't have this other motif over here, you're okay. So in this context, we will provide these with expert defined rules, and actually ours are based on, now they're based on exactly what enamine uses to build their virtual libraries. So the idea behind this particular model is, we're trying to build some generative model which basically can conduct a search in an implicitly enumerated space without having to do the explicit enumeration that these virtual catalogs do. And so this is a conditional sort of policy that learns to construct a synthetic tree from the bottom up by selecting as a retrieval task one of the many different building blocks, selecting as a classification task these reaction types, reaction transformation rules, and then sort of composing this graph structure. And so we can train this kind of model on hundreds of thousands of known molecular structures with known synthetic pathways. We can sort of do this enumeration ourselves. And once trained, the way that we apply it to optimization towards specific goals is just wrap the whole thing in a genetic algorithm, basically. Because it's a conditional model, we can just change that inputs so that it's no longer corresponding to an actual molecule we care about, but just some arbitrary numerical vector. That, of course, leads to a different set of actions, which is a different molecule, which is a different set of properties. And so that's now very conducive to model-free optimization with GAs. The effect of doing this is sort of exemplified by this case study of optimizing this heuristic bioactivity score. So this GSK3 beta, I think it's it's a random forest model classifying bioactivity 0 and 1. And if you use sort of fragment-based generative techniques, you end up finding very large structures that score quite well, but they're very large and not actionable. And sort of by virtue of coupling together the design of structures with the design of the synthetic process, this model finds a single-step reaction that leads you to a candidate that is scored by this surrogate oracle to be also quite promising. So we force this model to sort of think in terms of synthetic pathways, and that ends up sort of constraining the space, which gives us molecules that we can then take into the laboratory much more readily.
You also do something like yield in these reactions that yield is an underscore. Yeah. Okay.
Yeah, so in principle, you could start to consider yield. You could incorporate those considerations. In practice, we don't, because in discovery chemistry, yield doesn't really matter so much. So we don't do that, but for later stages of process development, when we're thinking about scaling and manufacturing, we certainly want to try to predict things like yield, which has its own challenges.
Does the synthesis plan that you generate actually ends up with what is being used to synthesize the actual molecules, or it ends up being different and you're just using it for like synthesizability scoring?
Yeah, so I think you could follow the route exactly, or you could just use this to triage and then give it to a chemist or a contract research organization to redevelop a route. But in principle, the reason why we would constrain it is so that we can follow that route if we so choose. And I think long term, not even going to say medium term, right? One could imagine coupling it to automation, where you basically have a very constrained set of reaction types that you believe that you can automate, and that way you can sort of follow those protocols more exactly.
It seems like with this sort of these different reaction steps, it almost kind of looks like similar to what people do for like shape parameters. So different types of way articulating like what types of shapes that together. Like have you looked at any of that literature? Is any of it helpful for the types of things that you're
I don't know that I have not looked at that literature, but that would be good to follow up about. Yeah. Thanks. So this model was again thinking in terms of sort of reaction generation. It's a bottom-up tree generator. It's sort of a hacks together sort of policy network, making a series of decisions. So of course you can just replace the whole thing with a transformer if you find a good way to sort of tokenize and linearize your reaction pathway. So we use a sort of postfix notation for synthetic process. We then train an encoder decoder to take a molecule that we'd like to make and then decodes the synthetic route that has been sort of tokenized accordingly. And again, because we need to constrain this model to use commercially available building blocks, we don't treat each building block as a distinct token, but we do predict into some embedding space and do a retrieval task with that. So sort of exact same idea, but replacing the decoder just with a transformer decoder ends up giving us this direct upgrade from the previous model. Now, something that's sort of fun, at least I think it's fun about this type of model, is that even if you give it a molecular structure or give it some sort of property condition and it's optimizing, and it's not making exactly the molecular structure you want, it's going to try, right? It's going to try to get close. And so that's sort of what these other columns sort of represent. So actually on our test set, this new model only exactly reconstructs the graph we encode 30% of the time. But overall, right, even when it doesn't reconstruct that graph, we end up finding structures that have very high similarities through a few different metrics. And so you could imagine, right, instead of viewing this as a 70% failure rate, you could say, well, what the model is doing is it's trying to find synthetically accessible analogs. And so it's able to sort of take a molecule as input, which might not exist in your sort of feasible sets, and then find, okay, well, what are the structures in your feasible synthetically tractable region that are close to it that you might be able to make instead. And so that's a use case that I think is quite appealing. in combination with generative techniques, you could then perhaps do the unconstrained optimization and then pass it through this to just say, okay, well, what's closest that I can actually make or that I could actually buy? Percent success here, this is should really be called percent validity. It's just the percentage of having a valid pathway be generated. Yeah. Where validity is following the rules of the templates and terminating in a molecular structure.
Synthesis library VAE, but atom-wise people?
Yeah. So so Atomwise had a recent paper doing this sort of reaction-based generation as well. Yeah. It's in the same family.
Okay. So is this, I should just think of this as quite similar, or is there some unique difference that's important?
I would have to go back and remind myself of their exact model design, but it's in the same family of synthetically constrained approaches. I think if I'm remembering right, the Atomwise one was truly looking at a combinatorial space of sort of synthons and how they could be stitched together, as opposed to allowing sort of many diverse types of reaction transformations to bring them together. But again, I would have to go back and look.
Do you get these kinds of success and reconstruction rates without any kind of RL fine tuning, or this is like just straight autoregressive prediction?
Straight autoregressive prediction. Yeah, just trying to encoder decoder. Yeah. All right. I might skip the third one because I think the fourth one is more fun. And the third one, I guess, all I'll sort of point out quite briefly is that the question of molecular representation is not a solved problem. I think in particular, the field has sort of really overbuilt itself on, for two-dimensional representation, sort of molecular graphs and covalent bonds, and this does poorly when we start to think about organometallic species and stereochemistry and things like that, but that's for another time. I guess what I'll sort of mention then last here is this sort of notion that really we don't do sequential, iterative, one-at-a-time optimization of molecular structures. Experimentally, we like doing things with parallel chemistry or on parallel plates. Computationally, we like to batch jobs that we send out. And so really when we think about doing molecular design, it should be treated as this batch problem. And so if we are willing to sort of buy into this argument that we're trying to find the best molecule in our design space, given some oracle, then one choice of the best batch would simply be the batch that maximizes the likelihood that the optimum is within that batch. I know that's one choice of many. But with this in mind, we've tried to develop some different techniques tailored to chemistry that try to get at this batch aspect. So one of the frameworks that we've been sort of building out to do batch molecular design is something that Jenna, PhD student leading this, calls Sparrow. The notion is that we can construct these very large candidate set of molecular structures. We can score them and evaluate them using different predictive models, different acquisition functions. We can also understand how we might synthesize them, or if we can just purchase them, the fact that we can just purchase them. And then on balance, we're trying to do this now sort of cost-aware optimization, right, where cost is considered at the batch level. So actually, before doing this, we were looking around at a lot of the literature around cost-aware Bayesian optimization, and I think cost-aware Bayesian optimization is relatively underdeveloped. And I think in this case, because we're talking about synthetic costs, there's also something special, because you might design two different molecules as candidates, and it could be the case that they share a starting material or they share an intermediate, and that overlap in synthetic processes contributes to a lowered cost, right? So costs are not additive when you talk about molecular design. And so effectively what we're doing with Sparrow here is we're trying to add this optimization layer on top of generative models, on top of property prediction models, on top of synthesis planning models to inform batched molecular design. And one of the sort of other benefits here is that we're trying to sort of put candidates from any source on equal footing, right? So if you have an expert at a whiteboard, if you have a generative technique, if you have zinc or enamine, you want to compare those candidates sort of apples to apples. And so we pose this as a down selection problem. So we enumerate all the synthetic pathways that we can find for all the candidates, and then we introduce a whole bunch of messy notation. We treat this as a big integer program where what we're actually optimizing over is sort of the choice of whether to run certain reactions and whether to include certain chemicals. So I'm not going to sort of talk through all the notation here because I really just want to convey the main themes. But we're deciding sort of which molecules from our large candidate set to make and what are the reaction pathways to make them, or if we can buy them, just the fact that we're going to buy them instead of make them. Now this ends up giving us a non-linear objective function, and so we, in the first iteration, wanted to linearize it, so we do that. We linearize, we scalarize, which changes a little bit how it behaves. But then qualitatively, what we're trying to do is we're trying to balance, right, the selection of molecules that have high rewards, molecules that are cheap or use cheap starting materials, and then if we have to synthesize things, we'd really like to make sure that those reactions will work. So we try to use the likelihood of success and not do too many reactions. And all three of those sort of categories build on these other predictive techniques that we use in molecular design. So again, rewards, those could be surrogate oracles, they could be computational oracles, they could be acquisition functions, cost or costs, we get those from vendors. And then the reaction pathways and likelihoods of success we get from various synthetic chemistry predictive models.
Non-linearity, do you mean in the sense that you're doing batch design and the reward requires you to look at them all simultaneously?
Yes.
Okay.
Yes.
So like sort of, which is I think always true in batch design. With any reasonable batch acquisition function.
Yes. 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 Yes, and I think there's the non-additivity of rewards, but there's also the non-additivity of costs. And in particular, the non-additivity of costs introduces some chemistry-specific considerations.
What's preventing this from just selecting almost like a batch of nearly identical chemicals?
Yeah, so in this particular case, nothing as posed is doing that. We've added in diversity constraints if you want to cluster your molecules and do things like that. I'll briefly come back to that idea of diversity in a couple of slides. Not with an answer, but with comments. But as posed, nothing would prevent it from predicting highly redundant compounds. In fact, highly redundant compounds might be easier to synthesize, and so it would favor those compounds.
Since you have expert feedback, what prevents you to use like reinforcement learning with expert feedback? Like you pre-train a model and then you have this reward from experts. Does it make sense in your case? Or?
To like fine tune a reward function? Yeah. Like in principle, nothing prevents us from doing that. I don't know how, let's say, sample efficient that could be in different contexts, because for every different drug discovery program, you're changing your objectives, you're changing your reward function. But I don't think anything is preventing us from trying that. Yeah.
At the beginning, you were talking about being unsatisfied by the kind of ad hoc procedures people have employed before and wanting to formalize them. And I appreciate that that's what you're doing here. I guess my question is how much you think writing this down formally as opposed to this batch selection procedure existing in some expert's head is making a difference. Like, how much does it matter in speed of discovery or in replicability or whatever that you could write this down as opposed to some person just doing it? Like, is it really?
Yeah, I think replicability, it matters a lot. In my opinion, I think we're never going to be able to convincingly show that one computer-aided design workflow is better than another without having systematic tests comparing validation rates between the two of them. And so to any extent that you have manual intervention, you sort of lose that ability to cleanly decide which is better. I think also in practice, when you have small candidate libraries, experts are okay at this, right? Experts can do this, that's okay. But when you start thinking about very large collections of compounds, it becomes harder. And in conversations, because we work with a bunch of pharmaceutical and chemical companies, they want these frameworks to help them make these decisions because they do think that they're not making them optimally. even in their own minds. They're doing the best they can, but now that they're seeing thousands or tens of thousands of candidates coming from generative models, again, they've got 40 billion structures they can order from mean to mean. They have their own ideas. They just don't really know how to grapple with that size of a candidate set to down select. It's a fair question. So I guess just as a qualitative example, and I know this isn't purely chemistry audience or medchem audience, one of the case studies that we looked at was this analysis of a design cycle where there were 121 different candidates, and based on the full set of assumptions and hyperparameters and preferences that can be set, one of the solutions that came out was to just buy 6 of these candidates because you can just purchase them, so you might as well. All the candidates that we are testing are shown in pink with their reward functions normalized between 0 and 1 below them. And then it suggested, okay, after you've bought those 6, you can synthesize 9 additional ones to test using a total of 6 building blocks and 10 reaction steps. So the qualitative thing to pay attention to here is that pink things are molecules that are in our candidate set that we believe we will get utility out of making and testing. Blue, just things that we buy. Black are just intermediates. And you can see that we are quite compactly designing this sort of network of compounds. So we're sharing intermediate structures. We're even sort of finding value in testing an intermediate before we get to a final molecule, and building that into the down selection of compounds, right? So maybe one of the reasons why we chose to make this molecule is because we knew that we could also gain value out of testing one step precursor to that. And so qualitatively, right, this is really what we're trying to achieve with this framework, is that we are generating this very large design space of candidate structures, synthetic pathways, and costs, and we are trying to now do this optimization where our design space, right, is basically picking the compounds, picking the reactions that we think are an optimal subset.
Just so you know, there's 7 minutes total left.
Okay, awesome. So one more content-y slide. So the final comment on this, sort of getting to this notion of sort of redundant compound selection and the fact that we want to think about diversity in batches. And when you look at the sort of manual interventions that are done in computer-aided design workflows, you typically will see diversity clustering or cluster based on a scaffold, and then you select cluster representatives, and that forms the final set that you make. And I think really everything that we do in cheminformatics that relates to diversity selection and clustering is really just a proxy, maybe a good one, but still a proxy for decorrelating the risk of failure, right? So that's why we sort of hedge our bets. If there are systematic biases in our computational oracle that we don't know, if we have diverse compounds, hopefully we at least will succeed somewhere. And so one approach to start thinking about this, and this is the last slide, so there's not going to be anything better coming after this, is to think about explicitly, right, sort of this batch construction with the sort of correlation or covariance of predictions in mind. And because batch construction is a hard problem, right, we almost always do it myopically. And so you can imagine that the first best molecule for your batch, if you again buy into this idea that we're trying to maximize the likelihood that the true optimum is in our batch, you would just find the structure that's most likely to be the optimal one. And if you estimate that with Monte Carlo integration and you have a sample of 1, you get Thompson sampling, right? And so maybe Thompson sampling sort of gets you satisfying that first molecule that you add to the batch. But then the second and third cases, I think really what you want to do is you want to make that batch selection decision conditioned on the fact that you don't already have the optimal compound in your batch. And this is, like the existence of this conditional here, I guess in some ways is subtle, but this is what separates this from sort of what people have been doing as sort of parallel Thompson sampling. Or for parallel Thompson sampling, you just do sort of many sort of sequential samples from your predictions posterior, calculate those acquisition functions or the surrogate oracle scores, and then you choose the top 1, 2, 3, 4, 5. But if you add in this conditional, then I think you're better capturing what you actually want to achieve. And so this means is that we are we're back to sort of being reliant and sort of limited by the ability to predict uncertainty and have sort of a proper probabilistic prediction of surrogate oracle values for our full design set. Yeah.
Is that probability being computed with respect to the probabilistic surrogate, or?
Yeah. So this would be using like a probabilistic surrogate model, but unless our computational oracle itself was probabilistic, then we could use that.
There is a little cottage industry in machine learning from some time ago that is doing non-independent batch design that you might want to think about.
Yeah, I've found some of it. I probably haven't found all of it, and so if there's any specific pointers. Okay, yeah.
Have you found that parallel Thompson sampling doesn't work well?
No. So this is also, yeah, so I think parallel Thompson sampling, I think in practice may work well. I think does tends to work fairly well. I think there are certainly like edge cases that you can construct, whether they're realistic or not, where it does very poorly. So
I agree, but
yeah.
almost all my applications we just do parallel Thompson sampling until we discover that it doesn't work well.
Yeah.
And that has yet to happen in a real application.
Yeah, which I think is a very fair point. Now I'm curious. So I know for some of those, last little footnote, when you have iterative workflows and you know that you're going to sort of repeat this process time and time again, then I think that also is a way of justifying Thompson sampling in the first place, right? Because you're doing this like horrible stochastic approximation to this probability when you sample your posterior once.
This is a one-shot batch, not a repeated batch.
So you could do either, right? I suppose. But I think the point is that like I'm trying to sort of distinguish in some of the like ongoing empirical tests that we're doing between the iterative case and the non-iterative case, because I actually think that a lot of molecular discovery workflows that use computational oracles or surrogates, right, to pick compounds are not iterative. You set up your docking pipeline, you set up your property predictors, you construct your batch of compounds, you put in an order with enamine, and you cross your fingers. Yeah. So you can do it very inefficiently by just sampling from your probabilistic model and doing basically rejection sampling. But more systematic ways than rejection sampling we're still looking at. Yeah. Because that can be very inefficient. But I think here, so there has been work, right, related to the sort of diverse batch construction. I think the way that it's implemented in the chemistry community is like very sort of ad hoc. And I think even if I accidentally reinvent something that was done like 40 years ago, which is not unlikely, hopefully there will be sort of better translations to chemistry that we can make happen. Yeah.
So here you're trying to predict the max, right? In a lot of these optimization problems, you just want to get a near optimal. So is it the case that in the application you get one solution that is way better than everything else, therefore you really find the max? Or is there, 100 solutions that are almost optimal, and I'm happy if I find one of those 100?
Yeah, I think often, right, you will have many compounds that perform similarly in terms of either a single objective or along a Pareto front if you're extending this to the multi-objective case. I think it's a question of what is the definition of optimality that you start with, right, to then motivate your acquisition function. And here, at least, I want to start with the goal of getting the true optimum. In practice, of course, even if you don't find that, you could still be doing something quite useful. But we can talk more about that, I think. All right, so we're out of time. I skipped some things in the middle, but I think sort of the overall message is I do think that computational oracle development is really one of the major challenges, and I do think it's incredibly difficult and requires a lot of domain expertise. I think that we will always continue to work with experimental oracles because that is the ground truth. We live in the physical worlds. And I do think that should constrain or at least inform the design space that we are searching when we do design of new molecular structures. And then again, in practice, we're not doing sequential one at a time design. It's either batched and sometimes, again, not iterative at all. We just have one shot of ordering compounds and testing them. But finish there. Thanks for the invitation to be here, and I'll acknowledge the group and funding.
Pretend to use the mic down. You say that it's often one shot, but surely if you do that and it doesn't work, you go to a second shot, right?
I think it depends.
Uh-huh.
I think it depends.
I see. I'm really curious. Like, can you explain in a situation in which you would just be like, well, that didn't work, let's move on? Like, that's what happened in industry, or like?
So I think if you do one shot and nothing pans out, in a lot of academic workflows, at least, you would say, well, perhaps my computational oracle or my surrogate oracle is just really not what I thought it was.
Yeah.
Or maybe I was doing, this sort of absolute binding free energy calculation using my cool new system, and maybe it just doesn't work that well for this protein.
Mm-hmm.
And so you might change targets, move on.
Yeah. Okay. Yeah.
But if you're in industry and if you really are convinced that this is a target worth going after, then you probably would revise your oracle and try again.
Worm, then hunter, then break.
Do you have any thoughts on or work on designing targets that have high specificity for a given target amongst lots of similar maybe protein targets?
Yeah, so we've done work using docking, which is shameful to say. Okay, we've done some work where we do optimize for selectivity. We use proto optimizations for this. The challenge is that for docking, this retrospective is not a good way of understanding how useful docking is. So what is more useful is having these prospective examples that I use docking, I picked the top compounds, and then I tested them experimentally. And if you gather all those anecdotes together, you start to build some notion of what is the false positive rate of docking. Right? Like, when does docking think you have a binder, but you did not? Right? We have that kind of data we can bring together from a lot of experiments. What we don't have is a good estimate of the false negative rate. And so we can't truly say because we don't predict a strong interaction between this ligand and this protein, we can't really say that that's clear evidence that it's a non-binder. And so I think, from the algorithmic perspective, we can do selectivity optimization, but from a practical perspective, I think docking is not able to confidently say when there isn't an interaction.
I was curious, it seems like a really hard part about working in this space is that it's really expensive and time consuming to synthesize molecules and test them in the lab. So I was curious what your thoughts are if someone in this room thinks they have a great generative model for drug discovery. Like, what would be a good convincing experiment to demonstrate that? Are there in silico surrogate models that you like, or do you think we need to just synthesize these and test them in the lab to convince anyone?
Yeah, I think I truly don't think there is any in silico demonstration that I would find convincing enough. I think you'd have to convince somebody that this is worth testing experimentally, and you'd have to have that sort of validation.
All right, we're already a little bit late, so let's wrap up. And we were supposed to reconvene at 10:40, but let's do 10:45 and shift the schedule by 5 minutes. And then we have a few short talks, and then we have Sarah Mostafavi, who will be giving a talk. So yeah, so let's reconvene in 10 minutes, which is 1:45. Thanks again, Connor. Thanks.